All right, one thing I showed you guys was the demonstration. What I did was I hung a mass off a vertical spring, and essentially what that does is that, stretches it to a certain point. But then what I do is I stretch it. I pull it down. And then what that does is that gives it potential energy. We release it and you get changes in energy as this thing oscillates up and down. So it oscillates between this point and then it goes up. This spring will get compressed and then it'll end up going back down. And then in the end, it's returned to exactly where it started. That's one full period right here. Now, from circular motion, we learned that that was a measurement in time. That's best measured in seconds. So, capital T is the symbol for period in this chapter as well. But now we're talking about a different event. We're not talking about a circular event. We're talking about an oscillation of a spring. Frequency, if you remember that, that's measured in hertz. It's 1 over the period in seconds. That gives you something in hertz, and the abbreviation for hertz was H, or capital H, in Z. Now, what we're going to find is that you can actually get this to happen with a vertical spring. You've seen me do demos in class with a horizontal spring as well. So you can stretch something beyond the equilibrium point. If I let it go, it's going to fly back that way. Remember, that's where it had maximum speed, maximum kinetic energy. Compresses the spring, shoots it back the other way. And what I've done here is I've diagrammed out one full period for a horizontal spring. And one of the interesting things that we're going to find here is that the oscillatory behavior isn't affected by whether it's vertical or horizontal. In fact, we saw some interesting things in the demonstration that I did. What we want to realize here is that the period, if you watch the demonstration, if you think back to what I did, it depended upon the mass that I hung off of it. And in addition to that, it's going to depend upon the strength of the spring itself, which is the spring constant. The formula for period is this. It's 2 pi times the square root of the mass over the spring constant K. So what I really want you to notice here is that at no point do you see anything for how far we stretch it down. What you should have picked up in that demo video that I did was that that didn't matter at all. I can stretch it a little bit, I can stretch it a lot, and it seems to have the same period. Because frequency is always 1 over T, what I can do is 1 divided by that, and I can get frequency. That would be 1 over 2 pi square root of K over M. So you have the ability to solve for the period and frequency if you have the mass attached to the spring and if you have the spring constant of the spring. And then what you saw is that as I put different masses on there, it should have affected the period. What ends up happening is that as you put a different mass in, that's going to affect the T a certain way. If you take a look here, it's in the numerator, the mass. So if I put a heavier mass in there, that's going to make the period larger. A lighter mass will make the period shorter. The other thing that we looked at was a pendulum. So basically, the simplest form of a pendulum is a mass attached to a string. And then if you just let it hang here, it's just going to hang here. But what you can do is you can pull it back. Now this is an energy thing as well, right? We got potential energy here. It's all converted into kinetic here. And then it gets converted back into potential on the way up here. So you see this thing oscillate back and forth. And then when your pendulum goes all the way to one end, and then all the way back, that is one period. What I showed you in the demonstration was that depends upon the length of the pendulum. What you should have found is that a longer string gives you a longer period, a shorter string gives you a shorter period. So we have formulas for that as well. The period of a pendulum is equal to 2 pi times the square root of L over G, where L is the length of the pendulum itself. This is L. So what you should have seen, and I did this, I put a heavier mass on there, didn't affect the period at all. There's nothing in there for the mass that's attached to it. It actually doesn't matter here. But what does matter is the length. When we shortened the pendulum, it got quicker. Made it longer, it got slower. And then G is equal to 9.81. That's a positive number here, meters per second squared. So what you find is that the fact that it's on planet Earth is going to determine its period as well. By all means, if you go to a different planet or a different planetary body, the value of G would change, and the value of its period would change as well. Because frequency is 1 over the period, you could actually rate frequency as this, and you can get the relationship of frequency to the period.